All right. So last time we started talking about the ball that we tossed upward. And we said that if we were to do this with kinematics equation, it's going to be a little difficult, right? Because we called this 0 here. Or wait, did we call this one 0? And this one 40? I think we did it this way. So this was our 0, 10, 20. So this was 0. This was 40. We had a height difference of 40 meters between them. So we were talking about how we would solve for the one that was tossed upwards, right? Yeah. Okay. All right. We said that our starting position here was 40 and our final was 0, right? You remember I was talking about that because of the way we defined it? So this one's going to be 40 over here. We had just kind of talked about how here our initial velocity is not going to be 0. So this is going to make our problem a lot harder, right? Yeah? Okay. I have some numbers that I actually solved for, so let me make sure. Yeah. All right. We're going to say that our upward velocity here is 3 meters per second. Everybody good? And I didn't tell you what mass was, right? Okay. We're going to say that mass is 1, just to keep everything nice and easy. So the mass is 1 kilogram. We've got an upward velocity of 3 meters per second. Pretty good? Okay. So what we're looking for, like I said before, is going to be our velocity down here at the ground. Okay, so we're looking for this velocity. All right, to do this, what do we need to find? It's going to be very similar to the other one. We need to find the time, okay? And because we know our two distances, our two positions, we need to start with that. Very good? Yeah? Okay. All right. So we are going to go down 40 meters, which actually, that's going to change my numbers. All right, so we'll have to redo this anyways. So I guess it doesn't matter what numbers I use. Let me pull this up so I can do this faster. All righty. So we want to solve for t, right? So let's at least get it so that this is over here. And so we're going to have good? Yeah. All right. Because I'm going to show you an easier way to do this where you're not going to have to use quadratic equation, I'm just going to solve it using a computer. Good? I'm sure you guys don't mind that too much, right? All right. So let's make sure that our numbers are in here correctly. We said that down is negative. Okay? So our initial position is 40 meters above, so it's going to be positive, right? Actually, if we're using quadratic equation, it doesn't actually matter because I'm putting it in the computer. Because if we were using quadratic equation, we'd actually want to keep this over here, right? Because that would be our c. Do you want to keep it over there just for ease, I guess? We'll just go like this. All right. So let's put our numbers in so that we can put it into the calculator or computer and make sure we have everything in the right spot. So we're going to have 0 meters, 1/2. Is our acceleration going to be negative or positive? Negative. This is going to be one of those where you are going to have to be incredibly careful with negative signs. If you get one off, then the whole thing is going to like start giving you imaginary numbers and weird things like that. Okay? That is another thing. If things like this give you imaginary numbers, you're probably off on a negative sign somewhere. Cool? Okay. All right, we've got t squared here. Our initial velocity is positive or negative? It is positive. We've got 3 meters per second times t, and our initial position should be positive or negative? Positive. All right, everybody see where we got all the numbers from? All right, let's put this in the computer and see what it has to say. Okay, so we get 2 roots, okay, as you would expect from an equation like this. We get t can equal negative 2.5662 seconds, or 3.17782. Okay? Now, do both of these make sense? No, they don't. Okay? So, this is one point where math and physics are going to be a little bit different. Because in math, if we were just doing this as a math equation, we would keep both roots, right? But because we are talking about a physical situation, and we don't want to go back in time, right? We know that for our situation, this root doesn't make any sense. Okay? So we're going to cross this one out. This is the time that we're going to use. Okay? What that other root is essentially saying if we had actually tossed it from the ground up and just knew that it was going 3 meters per second here, and we called that time 0, that would be our time in which we tossed it from the ground. Does that kind of make sense? So there might be a situation where this root would make sense, but in this case it doesn't. Cool? All right. So this is our time. Now we're going to take that time and put it in here, and we're looking for our final velocity. So we want to go negative 9.81 times our 3.17782 plus our initial velocity of 3 meters per second. So what do you guys get? Mm-hmm. All right, everybody good? Now, I think everybody will agree that this part right here is probably the most annoying part to do, right? Yeah. Once you get to this, plugging it into this equation is not bad. But there is an easier way to go about this, okay? And if you remember what we were talking about last week, what do you think it's going to involve? Gravitational potential energy. So let's do this now with gravitational potential energy. We're not going to need that equation. We're not going to need this equation. Okay? Is gravitational potential energy easy to calculate? Yeah. And since we have actually set this as our zero of gravitational potential energy down here, it's going to be even easier. Okay? So we know that our work done is equal to the change in gravitational energy, right? Yeah? So work is change in G. Okay? Work is also change in kinetic energy. Yeah? So what we're going to do is we are going to set our change in gravitational potential energy equal to our change in kinetic energy. Okay? So don't forget that when we have this delta sign, we're always taking our final minus initial. Okay? So our final gravitational potential energy here is going to be when we're on the ground. Right? Everybody agree with that? So we're going to have our mass of 1 kilogram times, so it's mgh, right? So times negative 9.81 meters per second squared times our height. Okay, so our final height is going to be 0. Minus, so final minus initial, our mgh, which is 1 kilogram times negative 9.81 meters per second squared times our height of 40 meters. Good? So that's our gravitational potential energy. Okay, now we can, which is 1/2 mv squared. Our final one, if we hadn't already solved for this, we're going to pretend we didn't. We wouldn't know our velocity at the end, right? Yeah, so we wouldn't know what it was. So we would have 1/2 times our mass in kilogram times our final velocity, which is what we're looking for. Okay? Not plus. Minus 1/2 our mass in kilograms. Then this would be times our initial velocity. Right? So what's our initial velocity?
3.
All right. Yes.
You have to have the mass in there because you're multiplying everything by what you actually.
Not really. No.
You know.
No, because it would cancel out. Because we can factor the mass out here, and we can factor the mass out here.
Okay.
So that is another thing that makes this a lot easier than what we were doing before, right? First things first. Our velocity shows up directly, right? So we don't have to worry about solving for something and putting it in another equation, right? That also automatically makes it much easier. We also only have it showing up in one spot, right? Which once again makes it a lot easier. Yeah? So you can already see that this is a lot easier, right? Yeah? All right. So here we've got a 0. This whole thing's going to go to 0. We've got 2 negative signs here. This is going to go to positive. 9.81 times 40 is, what do we get for this?
3, 2, 4.
We do have some kind of strange units going on. So it'll all kind of cancel out once we're done. Actually, no, we don't. We just have, the reason why we've got strange units right now is because if we multiply this by kilograms, we'd have joules, so we kind of cancel our kilograms out. It'll rectify itself once we get this side involved. Cool? All right, so we have 1/2 of our final velocity squared. And then we have 1/2 of 9, which is 4.5. All right. Everybody see how the units are going to be fine? Yeah. Okay. So we want to move this over to this side, so we get 392.4 meters squared over second squared, plus, because this is subtracted, so we need to add it, 4.5 meters squared over second squared. We still got the 1/2 of the final squared. Okay, so what do you get when you add these two? Then we're going to multiply this by 2 to get rid of that 1/2, which is going to give us
790.
Do you guys mind if I move up here? I know I'm kind of going backwards, but we're running out of space. So it's 798?
793.8.
Okay. So now we just need to square root both sides. And we get 28 point, what was it? 17. So don't forget that you need to square root your units as well. And shockingly, we get the same thing, right? Which one was easier? The second one was a lot easier, right? I know I wrote out all the steps, so like it looks longer because it took up most of the board, but that's because we use the computers to solve for most of the first time, right? Okay. So we can use this gravitational potential energy and kinetic energy to help with a lot of situations where it's kind of annoying to solve for it through kinematics. Cool? Yeah? Everybody good? Any questions? No? Now, there are going to be some times where solving for this using gravitational potential energy is actually going to be more annoying. So if you're asked for things like, how far did it fall and you're given a time, you're probably going to want to use your kinematics equation. Okay? That is going to be a little bit faster than using this, just because you don't have something that tells you the distance fallen. But if you're talking about velocities and you've got something falling just from gravity, this is going to work every time. Okay? Good? So you really need to look at your situation and see what's going to work best. I will tell you, if you go on and take calc-based physics in college, there are going to be a lot of times where using your energy is going to make your life a lot easier. Okay? I know not the first class that I took in mechanics, which is going to be the stuff that's a lot like what we're doing here. But it was the first class that was mainly only for physics majors. We spent the first probably 3/4 of the semester doing stuff with kinematic equations, which was really good for practice with math. And then as soon as they said, hey, you can actually just do it with energy, it made problems that would take a page of work take half a page or a quarter page of work. So in physics, there's a lot of times where if you come at it from a different angle, so instead of just using your position and velocity like you would for kinematics equations and using your energy like we did here, it can make it a lot easier. Cool? All right, any questions? No, you guys are good? All righty. Let's see. I did want to make sure that was clear. I know we kind of talked about last week, but that was quite a while ago. The change in gravitational potential energy for both of these balls or masses or whatever we decided they were is the same. Okay? Even though this one's a larger velocity, right? The change in gravitational potential energy is still the same. The change in kinetic energy, therefore, also has to be the same. Okay? So the reason why this one ends up hitting the ground with a smaller velocity than this one is because it started out with a smaller velocity. So to get the same change in kinetic energy, we have to have a smaller ending velocity as well. Does that make sense? Yeah? Any questions? You guys are good? Okay. Cool. All right. Do I stop this video or do I just keep it going? We'll just keep it going. All right. So part of the reason that this works really well is gravitational potential energy is a very special type of work, essentially. So changing gravitational potential energy does not depend on how you get between the two spots. Like I said, this is a very special type of force, okay? Gravity is going to be one of those special forces, okay? A lot of your field forces are going to fall under this category as well, but they are what are called conservative forces, okay? This is going to be a good term for you to know, because like I said, if you take this in college, this is going to be something that comes up, okay? Let me make sure I can see this on the live stream. Okay, so I want you guys to have this definition. So a conservative force is a force, I guess I'll just read it directly from the book. A force is conservative when the work it does on a moving object is independent of the path between the object's initial and final position. So we already talked about that with our gravitational potential energy. Doesn't matter how we get between those two spots, but your starting and ending position are really all you care about. Okay? That's why when we had the ball that we tossed upward, it didn't have a different gravitational potential energy change because it started and ended at the same position as the one that we just dropped. Okay? So, let me write this up here for you guys. this is the definition that's probably going to be most useful for you. There is another version of it that is going to be way more useful if you're talking about a situation where you're involving calculus. Have you guys started doing integrals in calculus yet? Okay, then I will explain how this is useful in calculus. So this is the same sort of situation. It pretty much says the same thing, but like I said, the wording is more useful for calculus. So we have a force is conservative when it does no net work on an object moving around a closed path. This means that it starts and ends at the same point. Okay. All right. Have you guys talked about closed path integrals and stuff like that? No. All right. So if we were doing calculus with this, we could set up an integral that goes around a closed path. Okay. And you guys have talked about how integrals find the area under a curve, right? Yeah. That's essentially what they do, is find the area under a curve. Now, whatever that curve is, it's going to tell you something about that. So when you integrate energy like this, it's going to tell you the amount of energy. Okay? If you integrate something physical, like a circle or something like that, it'll tell you the area within that circle, right? Yeah? It's going to be the same when we do something with this. So if we integrate over a closed loop, right, it can tell us information about the area enclosed in that circle or sphere or whatever it happens to be. Okay? Now, if we know that our net work done in there is 0, we can actually use that as information, kind of like we did where we said that our gravitational potential energy at the end is 0, right? So we just start with our gravitational potential energy, set that equal to our kinetic energy and things like that. So we can actually get equations for motion or a lot of other information when we throw calculus in here. Because when we integrate, we don't just get a number, right? We can get an equation out of that. So if we can say, okay, I have this weird sort of setup for this curve, but I have an equation for it, right? So it could be, I don't know, something like that. Would you want to try and do kinematics on any sort of motion like this? Yeah. But if you have an equation for this, which would be a pain in the rear to get an equation for a curve like this, but you could, right? So if you have an equation for this and you integrate it, you now have an equation for the motion of this object, and you know that since it's a closed loop, your integral, if you're using kinetic and potential energy, is equal to 0. That's a pretty useful thing to have, right? Because if you know several of those variables, you can easily solve for another one because now you've got an equation that's equal to 0, right? So that's why this equation or this definition is so useful when you know calculus, whereas when you don't know calculus, it's not really super helpful. Cool? All right. So for right now, our main conservative force, the one that you can always count on being conservative, is going to be gravity. Okay? Friction, definitely not a conservative force. Air resistance, definitely not a conservative force. Those, it's going to change based on the path that you take, right? That can be seen pretty easily if you, I don't know, have a room that has carpet and a room that has like tile or something right next to it, and you're trying to slide something over it. It's going to take a lot more energy to slide it over the carpet, probably, right? Yeah. So there, your path is definitely going to make a difference. Good? Yeah. All right. Questions? No? All right, the bell's about to ring, so we're done for today.